All right. Hello, everyone. Welcome to another episode of Quirkcast. This is your host, Tim.
And I'm Mikey.
And this is Sahil. Welcome everybody to a brand new exciting episode of Quirkcast. As usual, a few logistical things. If you're on YouTube and you happen to be mad chilling with us and watching this, do post any comments or questions you have on the YouTube channel, and we'll get to those and answer those during the episode. And if you haven't already, please join our Discord channel, so you can also mad chill with us even outside of these episodes, and we can answer your questions. So, without further ado, so Tim, I was recently watching X-Men, and there's a super hero or mutant or whatever you want to call this entity that can called Nightcrawler, that can teleport from one place to the next. And I was thinking, like, with enough genetic variation, is that something I can do? Like, can I ever hope to become Nightcrawler, or is that just a dream?
Yeah, I would say maybe not through genetics, but in the realms of physics, we actually have some sort of research paradigm that kind of achieves something similar, but so far not quite on a person level, but more on like the particle level. Well, of course, to some extent, if you can argue that a person is just made of, particles, right? So the first step would just be to see, can we teleport one particle? And then the second question is, after we try to teleport one particle, can we teleport multiple particles? And somehow
two is much harder than one.
Yeah, to some extent. But let's just say, so far, I mean, obviously, technologically, it's not possible to teleport use like. But if Sahil, you were composed of just one particle, yeah, it's actually quite plausible. It has been done, actually.
So you're telling me all I need to do is just become one particle, and then I'm
done. If you encode the entirety of Sahil into one particle, yeah, we teleport it. We're gonna need some experimental physicist colleague to set up a lot of experimentation up until laser beam, whatnot, and yeah, we can set up that experiment, quantum teleportation.
Wait. I'm pretty sure I saw on my Google News that they've teleported multi-particle states.
I wouldn't be surprised. Yeah. So
yeah, it's an engineering feat at that point, but I mean, the point is it's possible. Proof of concept.
What's so difficult about teleporting? Actually, like, why can't we do it? It's a limitation.
Yeah. So I think first we understand what exactly does it mean.
Yeah. Let's establish that first.
To teleport, like, what is teleportation?
Is it just really fast movement? Because, with Nightcrawler, you could argue that he's not genuinely teleporting. You could argue that he's, just moving so fast, imperceptible, that his movements are imperceptible.
Yeah, and also there's some.
That's one notion.
Yeah, but there are also some additional theoretical. Einstein's theory says that you cannot travel faster than the speed of light. So even though there are these physics experiments that does what we call quantum teleportation, we're still constrained by the fact that you cannot teleport something faster than the speed. The best we can do is, maybe a particle can go from one place to another at the speed of light, but on a silly. Because quite a few particles already do that. They move at the speed of light. So you can kind of question that, what is teleportation then? Like, it's clearly not just moving particles from point A to.
Oh, so then I ask you, Tim, what is teleportation?
Yeah, so some of this literature. There is kind of a more concrete definition, and it's actually quite simple. Instead of moving particles, teleportation is movement of information. Basically, is moving information about some object at the speed of light, one location, and in such a way that you can use those information to reconstruct, say, particles, basically, right? So that is, it seems kind of like, it doesn't sound so glamorous. It's like, you're just moving some stuff. Like, aren't we doing it all? Aren't we fiber internet? Like, what's up with that? But it's actually a little more subtle than you think.
I would think I'm already doing that somewhat on a computer. I mean, minus the signals don't travel at the speed of light, but I can imagine like sending photons instead of electrons through my computer. Wouldn't that be a form of teleporting?
Yeah, unfortunately, that would not. And here's why, right? Like, imagine Tim is made up of like, maybe you can kind of argue that all the information about me, my consciousness, my memory, or whatever, is just a bunch of information. And you can say, hey, how, it's like one of those Black Mirror episode, whatever. Put it in the cloud, go from send it through an email from one place to another, right? But it turns out that when you do that on a classical computer anyway, classical computer, when you make copies, it's not a 100% copy. You never copy all of it. For one thing, your copy has a finite size. It could be like gigabytes, terabytes, or whatever. Because classical computers have finite precisions, right? You can sort of imagine, hey, my memory of some numbers, like, 2, 3, blah, blah, blah. But really, in the real world, that memory is sort of stored in a continuous number. It's in a real number. It's irrational. It's got infinite precisions. Like, you can't pay for us to literally copy the internet. It'll take forever. So actually, the internet, or the whatever information teleportation we have, it's right. So this is where quantum physics come in. When we teleport quantum, when we say quantum, we're talking about quantum information. And these quantum information are defined by real numbers, complex numbers that have infinite precision. And when you teleport information in this way, you're teleporting everything about a quantum state to infinite precision, point A to point B, close to the speed of, like, that's what quantum teleportation, and that's why it's more, I guess, than just using the internet and emails. And
so for our listeners, can you at a high level, like, really quickly break down what is like this classical information, what is quantum information?
Wait, can I push back over that a little bit?
Sure.
Okay, because like, I feel like Tim is saying that the act of quantum teleportation is not similar to the idea of, like, sending packets through the internet, because of the fact that, when you send classical packets, there's some, you get some error rate, right? And that could accumulate. But I just wanted to point out that, like, from a process point of view, quantum teleportation is very similar to sending packets through the internet. But the ability to send, as Tim said, perfectly high fidelity, zero error, zero loss packets through the internet, it is, in a sense, the act of, like, deconstructing you in one place and reconstructing you in another place. And that is different from what a lot of people think of when they think of teleportation. Like, if you've seen, like, Nightcrawler, his teleportation is just, like, moving really fast, right? But what is a genuine teleportation? Is it like Back to the Future, like traveling through time? There are solutions to Einstein's equations that some argue will admit things like this, but when we talk about quantum teleportation and genuine, what I would call a true form of teleportation, it is this ability to deconstruct you and reconstruct you with perfect fidelity in another location. And it's surprising that this is possible.
I guess, like, going back to my original question about, can we briefly describe what quantum information is for people who are not as familiar with it, just super high level, like conceptually? Because when you talk about like teleporting information, is that different than like teleporting me or like the particles in me? What does it mean to teleport information?
I'm wondering if it's useful to distinguish quantum and classical information, because I think everything we're talking about could go through if you mix quantum and classical information together. The point is that, as Tim mentioned, when you send packets to the internet, there's some error. You're not sending the actual true full amount of the information. If you could do that, then it would be kind of a form of teleportation. And that's the main question. Can you perform this operation, like deconstructing me and reconstructing me at some distant place? Can you perform this without error?
Yeah, I guess compared to information, I wouldn't. Certainly, you can distinguish it in some formal way. Like classical information is denoted by bits, right? Zeros and ones, and then denoted by qubits, and then there's a lot of technical mathematics, linear algebra, and whatnot. I think on a level, we can sort of not think about those too deeply, because at the end of the day, classical information is quantum information. Like what else is there? I would say that classical information way of thinking about information. It's just like you're just thinking of averages. Let's say 1,000 quantum particles. The average location of them is a meaningful thing to talk about, and that's like class.
It's really if you say it that way, it's really a resolution, right? You're talking about like a pixel size.
Yeah, I mean, classical computers, they use particles, silicon, right? Those are ultimately quantum mechanical, but we don't care about those quantum mechanical properties. Computer chips are large, right? The electrical properties are based on averages of these particles. So really, huge averages of quantum information. That's what classical information is. When you look at zeros and ones, these are averages of some problem. And you're kind of coarse graining it in some ways, right? But it turns out that there's so much more information about a particle. I mean, obviously, when you deeply look at particles, it's not just that, a particle has a location property we call spin, up, down, left, right, something like that. Quantum physics goes beyond. It's more like beyond. And there's something called entanglement, meaning that when you add multiple, the sum, there's this phrase, right? The sum of the whole is much greater than the sum of the individual.
No, let me
combinations.
The way people see that usually is the whole is greater than the sum of its parts.
Yeah, something like that.
That's the phrase. Yeah,
I didn't frame it properly. Yeah, yeah. So quantum information just has to do, it's first of all of classical information, and in addition to that, there's entanglement. There's information in entanglement, and entanglement is gone we're taking these averages, but fundamentally entanglement so much more information than we're utilizing in our everyday world. Teleportation, we need to teleport those bits as well. Basically, we need to teleport the whole thing wholesale. So
I think to summarize, the task of teleportation we're talking about, Sahil, is can you develop an algorithm that can take apart Sahil atom by atom, particle by particle, transport it to another place, and reconstruct that from this pile of dust in a way that is exactly, perfectly lossless.
So I have a question about that. So if you're basically trying to teleport, there are going to be errors that arise from from the system. External events happen. Maybe a photon comes and mucks it up or something like that. You're gonna get these errors, and how would you know that you've copied with 100%? Because when you're measuring things, like us classically, when we measure things, we can't measure things to infinite precision. So how would you know that you actually have teleported, even like in theory? I don't know.
So when you're talking about like a photon possibly like ruining the calculation, that's actually not true. It does make it more complicated, right? So what you have to do to actually teleport you is I have to put a sphere around you and capture everything that could leave when it scatters off of you. That includes the photon. So once the photon scatters off of you, it's now entangled with you. It's now kind of part of you. Oh. And we have to track that. And so one way to do it would be to take a sphere around you and set off an atom bomb inside, so you get blasted to the exterior, and I get 100% of the particles. But then I would need a descrambling device that could take that mess. I'm very sure I have like 100% of Sahil encoded in this sphere where I set off the atomic bomb and blasted you to a billion pieces, but someone with access to that sphere could potentially write an algorithm to descramble you.
Yeah, so I think, let's say you really want to teleport to from point A to point B. Let's say point B is someplace in Andromeda Galaxy, whatever, right? You kind of have to have quite a bit of leap of faith. So if your friend who's trying.
Tim, one thing, our screensaver is on from the YouTube thing. So
okay, 1 second. Why is it on? Let me get that off. Okay. Why is it on?
Did you like colorful screen experiencing technical difficulties?
Well, it's just an Apple screen saying how to teleport through space-time, and it's it's back.
Okay, hopefully that will be fixed. We'll just try to cut that away. Okay, so I was saying, let's say we want to try to teleport Sahil. Okay, and let's go through different scenarios and different kinds of friends that Sahil had, right? So imagine Sahil had some classical physicist friend who are very capable, okay, and they say, hey Sahil, we're gonna break you apart, take all the classical information and try to reconstruct you with biology, genetics, and whatnot, right? And chances are Sahil is going to suffer a very gruesome death, got picked apart, his DNA sequence, and then they're just going to recreate another person who's almost definitively not Sahil, but then we'll have his DNA and be like close to Sahil, right? And we regenerate him, let's say in Andromeda. Like
that's a horror movie.
That's so if
Sahil, Frankenstein, actually, it's literally Frankenstein.
so that wouldn't be quite like actual teleportation, right? So, but then imagine Sahil, okay, talk to some quantum physicist, also highly capable, then what that might do is, first of all, they're gonna set up what we call an entanglement system, and let's say someone wants to teleport Sahil from Earth to Andromeda, because somebody could set up some laser beam to send really entangled particle, let's say a bazillion of them. So a bazillion of them are on Earth, and a bazillion of them are sent to Andromeda. Okay. And then we're gonna do some like finagling, physics magic to change our system, okay? And those changes are going to be captured at Andromeda because those particles are entangled, okay? Okay, but once this experiment is done, also, it wouldn't be pleasant for Sahil. He's going to suffer like a lot of experimentation, okay? But then now all the information is kind of somewhat scrambled up at Andromeda, and then we gather the result of the experiment, and so it has to be accompanied by some classical information, and we send a spaceship out to Andromeda, and then combined with that information, someone can actually reconstruct the information of Sahil. Now that sort of, and we construct, I don't know, somebody like Sahil. When you do that, that's a much higher fidelity type of teleportation. And I think in that sense, it's more like a genuine copy of Sahil. I guess from Sahil's your perspective, you're gonna feel like, holy crap, your body's breaking apart, and then maybe like, I don't know, your consciousness will go through some kind of a wormhole or whatever, and then you just reappear in Andromeda and be like, oh, I'm still alive magically, even though I suffer.
I never thought about that. What would that feel like? You would experience dying, and then at a locally unambiguous later point in space and time, you would experience the feeling of being reconstructed. That would feel so weird. Wow, I never thought about what that would feel like.
Yeah, so I think classically you wouldn't feel that. Sahil, I'll be sorry to say, yeah, you are legit dead. Like that was just Sahil number 2.
But quantum mechanics can save you.
Quantum mechanics can save you, and indeed it's very deep, right? So quantum mechanics has what we call the no cloning, no deleting theorem. Basically, it says that the precise information of Sahil, you can neither copy it nor destroy it, basically. So if you really truly reconstruct those information somewhere else, that's legit Sahil, because we couldn't have copied it properly. We couldn't have deleted it properly. So if we appear in a different location, for all intended purpose, that is Sahil, like, you know, as opposed to classically, we're just doing like a crappy job of copying, like a Frankenstein Sahil copy. You know. So,
and not only is it possible to make an exact copy of Sahil, but this theorem that Tim mentioned says that it has to be possible for someone to do that. No matter how no matter how far you go into the future, it has to be possible for someone to decode this.
Why is it possible? Like, why does it have to be possible?
Well, your information is essentially never destroyed; it's just scattered. That's one of the maybe lemmas of this theorem, is that in a very real way, when you die, you're scattered. You're not like over. And there's a theorem that says that you essentially have to be reconstructible.
Oh.
So who knows what happens after we die? Oh, is that what?
Let's not go. Let's not get ahead of ourselves, right?
It's crazy though. Think about that.
Does that mean sufficiently in the future, like we'd be able to recreate everyone whoever existed, or is that just like a pipe dream?
It would take more computational powers to go farther into the future, but after a certain point, it's all the same.
Yeah, I feel like if there's a universe overlord that has infinite, I don't know, like
simulator
physics prowess, or like, yeah, computational resources, reconstructing human life would probably be pretty far down the list, you know.
Yeah, it wouldn't be a good use of resources.
Yeah, it'll be like, you know.
Yeah, but it's in that sense, it's like it's kind of saved on tape, even if you never use those resources, right? And then is it really gone?
I guess, how would this computation take place? Like, if you had somebody who had like that much computational power, just
people are literally looking into that now. Like, what are the limits of this computation?
But I would like to add that it's not even, you shouldn't even think of it as computation. The bits, you know, if someone were trying to descramble the info about Sahil and trying to reconstruct him, like it's not like you're computing something. You're literally taking the bits of Sahil and re-scrambling back up.
No, people call that uncomputing, right?
Is that? So it's not so much like.
But it's literally the same as the computation. So I don't know.
Well, I guess to some extent that's the only real way of computation, right? Because a classical machine, the computation is pretty lame, right? You make some loose copy with finite precision, and you just try it again and again.
No, but it's the same principle. I mean, in classical computers, you have on computation algorithms. It's how do you restore the memory and make it reusable again?
Yeah. Well, although one thing to add is, inevitably there's going to be some form of error. Like all these teleportation like achievements, like in China, there's a few other countries in US, and actually I don't know. I'm not too familiar with the literature. Most of them have some error rate. The fidelity isn't perfect. So Sahil, if you really want to teleport, that's you got to have some leap of
Wait.
faith.
Let's be clear though. The reason is because that comes from the fact that you can't guarantee you have every single photon that interacted with the system. It's like if in a that's a hardware issue, right?
Yeah, to some extent. So chances are we're very unlikely to surpass that, anytime in the near future. But
but where are you gonna go to that?
Oh well, I mean, especially for Sahil, you have so many particles. Even like a 95 success rate, when you have to do the same thing for like 10 to the 20, 30 particles. That I don't even know how many. That's a tough bar to clear. That's
well, if you're using hardware that is made out of it's almost like trying to build like a watch gear system using parts made of Lego blocks, right? Like the parts have to be smaller than the thing you're trying to build. So as long as we're using classical hardware to do these quantum experiments, there's always going to be some error rate, but that's coming from the classical side. The dream of quantum computing is to essentially be able to manipulate particles, use particles to store the information instead of these ones and zeros, these electrical signals and wires. So that's why I always kind of like laugh when people talk about using quantum computers to do encryption and decryption. It's easier to make a universe than it is to decrypt a password. Because literally, if you have a quantum computer, you're essentially using particles, fundamental particles, to store the information and manipulate and do computations that way. If you can do that, then you can easily teleport from one place to another, at least within the computer. So the question is, how big is your quantum computer?
So you're saying that, so what I'm getting from this is that theoretically it's possible to teleport in this way, but pragmatically just like it's probably not going to happen anytime soon because you need to keep track.
Inside a quantum computer it can happen.
Yeah, I mean, in the literature, people have done teleportation through like hundreds of kilometers. It's like they have some device to send laser beams which entangle some light particles, photons, from let's say one island to another, and then they could do basically quantum computation to muck around and teleport the information of an extra particle from point A to point B. So those have been done with like 90% fidelity, or there probably some like more complicated configuration that they have tried. So that's already a reality that's been done.
But I would say, absolutely zero error quantum teleportation of the kind that Tim is talking about can only be achieved inside the physical apparatus of a quantum computer. Quantum computer is literally, its job is to teleport information from one place to another. If we're saying that the analogy of transmitting information classically, transmitting information in a quantum mechanical way, if you think about it, a quantum computer is literally just sending quantum information in an error-free way from one point to another inside the computer.
Yeah, although I would say a lot of people might argue that that's not so much about teleportation. It seems like it always has to travel some distance. At least that's the general feeling some people have, right? Like,
yeah, but if you look at any quantum circuit, it is a complicated form of teleportation in the end.
I mean, of course, there's the other aspect of teleportation that we can think about is the idea of wormholes. Like you could, I mean, we talked about it in previous episode, but if you imagine there exists some kind of a wormhole from point A to point B, and you just jump into the wormhole, like I don't know, like one of those Marvel heroes, right? You can just make a portal. That's kind of like teleportation, sort of.
And I would just point out that a wormhole is very easy to simulate on a quantum computer. You could easily write an algorithm to simulate a quantum wormhole and do little teleportation experiments inside your quantum computer, and that would actually be a genuine form of teleportation in the way that we're talking about.
Yeah, Well, I mean, if our listener follow our previous episode, it was that the previous one about wormholes.
It's not in the second.
Oh, it's not the previous. Yeah, one of the other episodes about wormholes. It turns out that there's this perspective where wormholes are equivalent to entanglement. So in a very real sense, if this conjecture is correct, it's called ER equals EPR. That means that teleportation right now using entanglement is basically the same thing as literally some particles going through a kind of like a microscopic wormhole and we appear on the other side. Like it's very real. So the two might be, two sides of the same coin, basically.
I think the smart money is going in that direction.
So we have an audience question, and I'm gonna ask this one to you, Mikey. So can we create avatars of ourselves within this quantum computer and then manipulate the universe to give our quantum versions their favorite ice cream?
Wait, it's not a quantum version, let's be clear here. It is the same version in a quantum computer.
Wait, you can't copy it. Sorry, you cannot copy yourself.
Yeah, these aren't avatars. These are genuine.
These are you. Okay. Sorry, your avatar is you. If you create the avatar, you have to be destroyed because there's no copy and no deleting theorem.
Yeah, they can't exist at the same time. So it's like an avatar, but one that cannot exist at the same time as you, and that is kind of what makes it a genuine copy of not genuine copy, a genuine you.
I mean, you can do a crappy copy job, I guess. You don't have to copy precisely.
No, actually, that's interesting. Is that true? The fact that your avatar and you cannot exist in the same light code, in the same causal sphere of influence, is really what makes it a genuine you, not just some Frankenstein copy of you.
No, but there could be a crappy copy. There are these universal.
Yeah, but that's not what they're talking about, right?
They're universal quantum copying devices, but it makes a crappy copy. It means that there are definitely going to be some errors. So you could have like a Frankenstein avatar.
We have a high standard now. We're talking about Planck scale pixels. Like that's possible. Let's keep our standards high.
Yeah, then it's not so much about quantum computer. I guess you can say if you jump into a black hole and then some Hawking radiation comes out and someone try to reconstruct you. Well, that's not quantum computing. That just is, the world, right? So I don't know. Yeah, this is tricky, right? You can't. It depends on what you mean by avatar. It's not quite avatar. It depends on what you mean, I think.
In case there's any confusion, just Tim was talking about if Sahil is one particle, we could teleport him. If Sahil was 10 particles on quantum computers today, you could simulate him on memory and teleport him to the hard drive.
So all I need to do is reduce my number of particles and become less particles.
We need better quantum computers. But it gives you a sense of what will happen if that ever happens. And that's why actually, personally, I'm a little skeptical about, when people say this revolution is happening soon. People don't understand. If we really master quantum computers, we'll be gods. It's not an easy feat. It's not something that's going to happen quickly in the next few years. So,
wow. Well, maybe demigods, but yeah. So I guess like we're running up close to time, and so what I'm getting from this is that yes, you can teleport in a quantum mechanical sense, but it's just incredibly difficult because you need to keep track of everything that's entangled with the thing that you want to teleport.
Yeah. Let's just add the only genuine way of teleporting is the quantum mechanical teleportation.
Yes, that's important. And I would also add that it's surprising that it's that easy.
You mean like if you can do it in a quantum computer in that sense?
Yeah, the fact that it's possible at all, I mean, it's not, it wasn't obvious to people for a long time.
I see. Anything else you guys want to add before we head out?
Yeah, no. I guess. Yeah, it's just the when people talk about teleportation, there's all these these sci-fi imageries on like, oh yeah, it's like in Star Trek, you just press a button, you disappear, and you reappear somewhere else. And then it raises all these philosophical questions. It's like, hey, when that actually happens, is that you? Is that final you? Like, or maybe you just died and reappeared, or like, what gives, right? And there's all these, philosophical conundrum people were confused about for a while. And it's so interesting that, if you really think about the physical world, which is inherently quantum mechanical, it solves all these ambiguity for you, right? Because there's no cloning, no deleting. So if you genuinely teleport, yeah, that's you, in every sense of the world, in every sense of the word. So I think that's another instance where if you ask good physics questions, you kind of get like a good answer. Otherwise, it gets all messed up. It's like, philosophy, does it make sense? Does it not make sense? But but anyway, I guess the conclusion is, yeah, you just have to think about this question using physics, really, and think really hard, and then you get the right answer, which is, unique quantum teleportation. To really talk about teleportation at all, and it turns out it's possible, at least theoretically.
Actually,
yeah,
go Mike. Sorry.
Oh no, the only thing I'd add to that is I don't think Tim impressed upon how like the way of the right way of thinking about these kinds of things, in the way Tim was alluding to, is something that's really only started to happen like the last few years. And so it's really exciting, and just from an observer standpoint, watching this come together, because if you think about the questions that people were asking like 7 years ago versus the questions that people asking 2 years ago, they're of a totally different nature, and it's kind of creating, I would say, a mini revolution in the field.
Yeah, it is really exciting. Now, Tim, since you mentioned philosophical questions, I'm encouraged to ask you this one philosophical question, just to gauge your perspective. I'll say what it is, and for the listeners, just to give them full context. The ship of Theseus, or I don't know.
That's exactly the analogy.
Yeah. Or Mikey, if you know more about it, if you could explain it, and then like.
Wait, Tim, are you familiar with that?
Whatever.
Tim, are you familiar with the ship of Theseus? I don't know.
Somewhat. At least Sahil, you should finish describing
so it's like where you're in a ship, and then let's say you're traveling through the ocean, and you keep replacing all the parts, and then you end up with all the parts replaced at your destination. Is that the original ship, or is that different? So from like a quantum mechanical perspective, and based on what we're discussing, what would you say to that?
Wait, can I just say one thing? Okay, just quick answer, because I can't. In order to genuinely teleport, according to that analogy, every single piece of me would have to be replaced in order for it to be a genuine teleportation. Meaning, like the ship is completely picked apart, and then let's say those pieces drift apart to some beach, and someone collects every single last piece of those and reconstructs it. Yeah, I haven't fully teleported until every single last piece of the original ship has been reconstructed on that beach.
But then what about the new ship that's made up of these new parts, but it's still like has everybody on it?
That's the Frankenstein. I mean, that's not a Frankenstein copy. That's
Yeah, I would say that, okay, if you think about it quantum mechanically, and let's try to define what the Theseus ship was, right? It's a state that evolves. And part of the evolution is that some of the bits, some of the parts it had was replaced. And I think the ship of Theseus was not defined by any one instance of the state. It's defined by the entire trajectory of that state, right? And so if you were to talk about any instance of the ship, whether it's the ship of Theseus or not, that's a misnomer. I think you talk about
Wait,
the
but-
whole. If you talk about the whole trajectory of it,
You have
And-
to include the trees that made up the new pieces. So if you think about it, there were two copies of the ship all along.
yeah, to some extent, eventually, yeah, the ship came to be.
Yeah.
So
The
to some
ship
extent,
and the tree become the ship and the tree again.
and ultimately, because of the no cloning, no deleting theorem, there was ever only one ship of Theseus, and it's the entire trajectory of that ship through space-time. That's it. That's
Yeah. If you think about it, the lumber that made up the new pieces were converted into the new ship, and the old ship was teleported. That's a very apt analogy, I think.
Oh. All right. Well, I guess then that ship that comes out is not the ship of Theseus, or like is entangled with the original ship of Theseus.
no. I mean, the original was gone. The original is part of the new. Because first of all, you cannot make a copy. Like you can't say, "Hey, I get the same wood to make a copy of the ship," because of the no copy theorem.
Oh yeah, it actually says that
So-
the ship that you make can't be exactly the same as the original one.
Yeah,
but
it just
the,
has
the,
to be-
The one on the beach can be exactly the same as the original one.
Right, so the only way- The only way to define the ship is just to say that's it. The whole trajectory of the evolution of the ship is the ship, and there's only one and only ship. You can try to make a duplicate, and that wouldn't be a sincere duplicate.
People call us a paradox. That's ridiculous. We just
That's
solved this
ridiculous.
in
I think if you look at the
physics,
The physics is clear. I think if you get the right physics, you get the right answer.
but it is really cool that these questions were not so easily answerable, let's say 10 years ago.
Right.
And,
Yeah.
and now we have very, very precise answers to these questions. That's really cool.
Wow.
Yeah.
That's really amazing. When I first heard about this, I was like, I don't know how to answer that. But now you give me the tools to answer this question. So I think on that note, we should end here, and I want to thank all the listeners for joining us. And we'll see you all next week.
Yeah. See you all next week.